All right, welcome back to another episode of Scientifically Simple. For those of you who don't know, my name is Brandon. I'm joined today with Mohammed Fowd. We are going to be talking about the equations of state in a historical context and how they interrelate to the different fundamental laws of thermodynamics. Go ahead and take it away.
Well, on a side note, Brandon, you can potentially call me Mo as well. Thank you. Thanks.
Every other episode, you're just gonna go ahead and bring that up. You're like, oh, by the way, I go by Mo.
I go with Mo.
Even my advisor calls me Mo.
Absolutely. Yeah. I mean, yeah. Just for take that as an example. Okay. Well, thanks, Brandon, for this introduction. Today gonna be like we are going to go through the second episode regarding the package for the thermodynamics, and we are going to be covering in our clip today a quick recap on first law of thermodynamics, the equation of state, motivation, and history. Then we take what we have learned today and substitute into the first law. So for a closed system, neglecting any contributions like kinetic and potential energy to the system, we can write the change of internal energy of that system as a sum of heat extracted or added to the system while the work done on or by the system. As that work was done by a force over a distance, that's proportional to the pressure over a given volume. And from calorimetry experimentations, it was found that there was a correlation between heat and temperature. That correlation was named specific heat at constant volume due to the calorimeter setup which was taking place at constant volume. Substituting into the internal energy equation, we concluded that internal energy as a state function is dependent on system volume, temperature, and volume. Then a new variable called enthalpy was defined as the energy due to kinetic energy of the molecules in the fluid, in addition to the energy required to push that fluid into or out of the system. By simple differentiation, we can find out that dH would be equal du plus bdv plus vdb, which leads us to writing enthalpy being a function of pressure, temperature, and volume of the fluid. Then the next logical step was to be asking, is there any way that pressure, temperature, and volume has any interdependency, or are they truly independent of each other?
Right.
Which takes us now to the equation of state history. So Evangelista Torricelli, I hope like I'm saying his name correctly,
Say
who was a student.
Time?
Evangelista Torricelli. Yeah, I always like get confused about that.
Yeah.
Who was a student of Galileo, by the way, invented the parameter
that's cool.
in 1643, and the torr as a pressure, that unit was named after him.
That's cool.
Henry Power and Richard Townley in 1661, they used the parameter to be measuring the pressure of air at different altitudes. As a result, they have recognized there is a relationship between the density of the air and its pressure. So Power eventually published the result in his book called Experimental Philosophy in 1663. Then later in 1662, Robert Boyle was able to be publishing what's now known as Boyle's Law, but in reality he referred to it as Mr. Townley's hypothesis. So he actually, when he did that law, he actually give the credit to Townley, but somehow, historically speaking, we came later to be naming that Boyle's Law.
Right.
Edmund Marriott is particularly well known for formulating Boyle's Law independently of Robert Boyle. So as everything recorded, looks like he independently did find that law. So Jean-Louis Gay Lussac in 1808 discovered the law of combining volumes and published it in 1809. And in an honest move and an ethical move, he actually cited earlier unpublished work that was done in 1780s by Jacques Charles. So pretty much cool. Like Jacques Charles actually had that formulation, and that's why you have Charles' law, by the way. And basically, Joe Lussac was the first one to document this and publish it. Consequently, the volume temperature proportionality is usually known as Charles' law. Now, Avogadro in 1812 found out that two given samples of a gas of the same volume at the same temperature and pressure contains the same number of molecules. And that's literally what Avogadro's number is. So, with that being said, now you have like those pieces of the puzzle, each one independent, like measuring a given variable as a function of another variable, holding other, the rest of the variable as parameters. Then comes like our favorite dude, which is Emile Clapeyron.
Yeah,
that we have spoken about him last time, which we were talking about, like again, the Carnot cycle and how he was doing the PV diagrams. Yep, that's the guy that had to be going through all these laws to get them together. And basically,
that's very cool.
Yeah, he is the one that proposed combining Boyle's, Charles, and Avogadro's laws into one form that we know today as the ideal gas law, and that's how the equation of state came to existence.
That is insane.
I know. It's just like it's really cool how like everything comes
really cool.
Logically into pieces. However, there was a severe limitations associated with the ideal gas law. The gas should be given that law, the gas should be able to be condensed to a volume of 0, since the particles of perfect gas have no volume. However, real gas particles occupy space. So that's one piece. The other piece was like when the gas is condensed, it turns into a liquid state with volume. Because the substance is no longer a gas, the gas law no longer applies to it. Real gas particles are attracted to one another.
Right.
As the gas cools, its kinetic energy diminishes, causing the particles to move slowly enough to condense due to attraction force. In his 1873 thesis, van der Waals noted that the non-ideality of real gases and attributed it to the existence of intermolecular interactions. He extended the ideal gas law to include the non-zero size of gas molecules and the interactions between them, both of which depend on the specific substance. As a result, this equation provided the following. It was providing the existence of critical point, liquid vapor phase transition, including the observed metastable states. It was able to be getting specific heat at constant volume can be shown as only function of temperature, which was the first. Because nobody knew by that time if the specific heat at constant volume is partially function of temperature or it's literally only dependent on temperature.
Right.
Established the law of corresponding states. Those compressibility factor charts, that is basically thanks to that equation. Joule-Thomson coefficient and the associated inversion curve which was super critical in the commercial liquefaction of gases. And for that, in 1910, he was awarded the Nobel Prize in Physics. So, and since then, van der Waals equation of state has been invented, the equation of state that was following that has been based on the same core principle provided by van der Waals. And that includes the virial equation of state, Pink-Robinson, Suave, Erdős-Kwong equation of state as well. So basically, it's the same concept,
Right.
like Van der Waal have established. So now, with that being said, now how can we use what we deducted so far to be used in the first law core equations? So, given we have an interdependence between pressure, temperature, and volume, where defining 2 automatically define the third variable, both enthalpy and internal energy for a single component system can be a function of only 2 state variables, not 3.
Right.
That leads us to construction of phase diagrams such as that one that show for ammonia. And because of that, I can basically say, hey, enthalpy can be completely defined by pressure and temperature. And that's how we can mathematically model all these phase diagrams. So now, to summarize everything that we talked about today, enthalpy and internal energy are state functions. Pressure, temperature, and volume are interdependent, specifying 2, the third can be determined. Equation of state is the reason why thermodynamic state functions such as internal energy and enthalpy can be stated as function of 2 variables. Van der Waal equation of state was a first and played a pivotal role in describing properties of pure substances and mixtures in liquids and gases. Van der Waal formulated the first cubic equation of state with core foundation upon which all current equation of states are based. And with that, we conclude our discussion about equation of state. Next clip will be about the second law of thermodynamics. I hope this was an added value to our audience. Please feel free to contact us if you have any questions. And the mic is yours, Brandon.
Yeah, as Mo said, we want to thank you again for your time today. As you'll notice, this is kind of a shorter video. That's really the direction we're kind of taking things. A little bit shorter, a little bit more specific to the content we're trying to deliver. So if you enjoyed this or anything else we do, we ask you to leave a comment, leave a review, like, subscribe, however you might follow us. If you have any questions, send an email to sciencemadesimple@outlook.com, and be on the lookout for that next clip where we talk about the great evil, entropy.